Let's analyze transient conduction in an infinite slab with convection. Infinite slab, which is a plane wall. Assume that we have a plane wall with the thickness of 2L. X, this is L minus L. That initially it is at temperature Ti, and then all of a sudden, both sides of the wall are exposed to a fluid at T infinity. So we have convection going on both sides with the fluid at a certain temperature, and all the properties are constant. So what we have is the thickness is 2L, K, rho, and C for this plane wall are assumed to be constant. Initial temperature of the wall is Ti, and both surfaces are suddenly immersed in a fluid at T infinity at time 0, where Ti is different than T infinity. So if I put the axis X, Y, and Z here, starting from the general heat conduction equation in this Cartesian coordinate, we have second derivative with respect to the X, Y, generation, assuming there is no heat generation. And since this is the thickness is much smaller than the other dimensions in the Y and Z directions, we can assume conduction happens only in one direction. So we ended up with the 1D diffusivity equation. Now, in order to progress, we define theta, which is T at any location inside this wall that we have, minus T infinity. And initial condition would be is theta I, Ti minus T infinity times 0, and for the whole domain. This is the initial condition. If we make it temperature difference, time and less dimensionless, by making temperature, time and length dimensionless, in a way that dimensionless form theta star is theta divided by theta I, T of X and T minus T infinity, Ti minus T infinity. And if we use diffusive scaling for the time, T divided by L squared divided by alpha, which is alpha t divided by L squared. This is a dimensionless number, and that's the definition of Fourier's number, FO. And for x, let's make that dimensionless, 6 divided by L. So when I'm putting star in close to any parameters that we are using, it means it's dimensionless. Now, if I plug in into the diffusivity equation, then in the dimensionless form, it's going to be FO. So the solution to this one, theta star, would be in the form of function of x star, t star, or Fourier number, and Wyatt number, as we will see soon. So initial condition, theta star at x star at time 0 is going to be minus t infinity, minus t infinity, it's going to be 1. For t star or Fourier number zeros, and x star between 1 and minus 1. For boundary conditions, the first boundary condition, we're just going to put it A, or let's put it 1, is convection at the surface. So remember, for heat conduction at the surface is HA T minus T infinity. The amount of heat that is getting convected from the solid to the medium is equal to the amount of heat that is conducted through the medium. So Newton law of cooling, HA delta T, is going to be KA dt dx at x equal to L or minus L. There is a symmetry here. So if I want to convert this one to the dimensionless form, first of all, we have dt over dx, and dtx is going to be d theta over dx. Theta was t minus t infinity, and converting that to the dimensionless form is going to be theta I d theta star divided by theta I. And here I'm going to have L dx over L. So these are equal to each other, and it's going to be theta I over L d theta star over dx star. Now, if I replace that one in the top equation, HA T minus T infinity would be KA theta I over L d theta star over dx star at x star equal to L, x equal to L or x star equal to 1. And this one is going to just cancel out here. So if I do rearrangement here, t minus t infinity divided by theta I, this is definition of theta star or dimensionless temperature. We have HL over K would be d theta star over d x star at x star equal to 1. So this is theta star. So what we are going to have, and this is definition of Wyatt number. So what we would have here is, in terms of boundary condition number 1, in the dimensionless form would be d theta star over dx star at x star to cut 1. It's going to be bi theta star at x star 1 and t star, or Fourier number. For boundary condition number 2, what we can use is the symmetry at the of the temperature profile. So what we have is a solid, let's say this is the center line, and this is L minus L, and initially it is at Ti, so let's say this is Ti, and it starts losing heat to the surrounding medium, so it starts to cooling off from the side initially, and temperature reaches to T infinity, and as times goes by the temperature starts to decrease. But what happened here is cooling is going to continue, but what happens here at the center line, you're going to have always symmetry. So it's going to be a mirror images of the right side is going to be mirror image of the left side. So there is a symmetry always at the center. At the center, always the temperature would be symmetry. Then what does that mean? I'm going to write it down. 3 center line, symmetry of temperature. What does that mean is dt dx at x equal to 0 is going to be 0. Or in the dimensionless form, d theta star over dx star is going to be 0 at x star equal to 0. So we have two dimensionless, and the solution will be a function of, for this equation, function would be the function of the solution is going to be a function of x star that we have, Fourier number or T star, and Weyl numbers that is coming from the boundary conditions that we had here. And it's going to be in the form of complex series. Be a function of x star, Fourier number, Weyl number, in the form of complex series. So if you look at the exact solution, you will see that it contains many terms. Now we can get a good approximation, so I'm just gonna write it down. Approximate solution for Fourier greater than 0.2. Fourier is a dimensionless time, so it means for a time not close to 0, slightly above that, where the dimensionless time would be 0.2, we can use the first term of the series, that we have this complex series only as a good approximation. So the exact solution will be equation 5, the form of series. It's going to be equation 5.42a in the text. Now for this approximation, if we just take the first term here, what we are going to have is theta star of x star and T star or Fourier number be C1 exponential of minus psi square 1 Fourier cosine of 1 x star. So this is going to be the approximate solutions for Fourier when Fourier is greater than 0.2 or T star is greater than 0.2. Now, if you look at this solution, this part, this is the variable with time. So remember theta star or dimensionless temperature or temperature is a function of time and space. So this is the functionality with time. And the second term shows the variability with space. Here is x. Temperature at the center, can find out temperature center line or at the center of this wall where x star is equal to 0. If you put x star to 0, then the first term would represent the temperature at 0. So theta star of 0, 0, and T star is going to be C1 exponential of minus psi 1 square. So essentially in this approximation solutions that we have, this is going to be temperature at midpoint where x star is 0 or x is 0. So we have the temperature that is function of time. The midpoint temperature is just dropping as time goes by. So in another time, if I just make a plot, we're going to have the drop of temperature at the center line. So this center line temperature, this is increasing time. It's just dropping. And the rest of the point is a function of that one by the second term that we have. Now, how do we find the value of C1, like the constant C1 and Xi1? They are C1 and Xi1 are in table 5.1 of the textbook that we have. So in that table, table 5.1, if you look at that for each, in this table, what we have wide number, which is HL over K. You have the value of that. And the same thing, we have this Xi, the dimension of radian. You have the value for each wide number. You can read what is the Psi, and you can read the number of C1, the constant of C1. So you can find a value. Now, a quantitative picture of, like qualitative picture of the changing temperature profile, as I was plotting qualitative picture of changing temperature inside the wall, the profile, based on the solutions that we are finding, would be, let's say I have this wall and this is a x. Let's assume I'm plotting, this is temperature that I'm plotting here. This is L minus L, is starting from initial temperature of Ti. So assuming everywhere initially is Ti, then what we are going to see here is conduction inside the solid. So let's say now it's been exposed to temperature of T infinity, which is here. It's smaller temperature here. So when this wall is just immersed in this fluid, what happens is the heat starts to convect from the surface of that. So the temperature is dropping. So initially we would see a drop in the temperature on the both sides, and everywhere else is going to be Ti. And then the temperature is just convecting out of the system. So the convection would happen on both sides of the system. Now, as time goes by, the temperature starts dropping. So let's say at a later time, what we are going to see is, I'm trying just to plot it as a symmetry here. And I need to, and if you look at it the later time, this is again, we have a convection outside the wall. That's happening. And if you look at the later time, and again, convection to the outside. And eventually, if the time goes to infinity, then we are going to reach to exactly T infinity. So the convection continues. So this is the temperature inside the system, and that shows the increasing temperature. So this is the way the time just goes up, and this is the profile when T goes to infinity. At the final stage, we are going to reach to the T infinity. A quick note here is, let me just add the note. The solutions that we have found is for a plane wall. The solution is for a plane wall or infinite slab. Infinite slab to determine the transient response of a plane wall. So the wall or the solid slab to a sudden change in the surface temperature. To a sudden change in the surface temperature. Now, here what happens is we say we are just immersing that in a fluid with the temperature of T infinity and some heat transfer coefficients H that is just flowing on the both sides. But let's say if I say, you know what, we suddenly change the surface of this temperature to some values like Ts. Again, this solution is going to be valid for that situation too, for the surface temperature, and it's equivalent I'm just gonna put here is also valid, is also applicable. We started from the convection from the surface of the wall, but this solution is also applicable for the system that there is a sudden change in the surface temperature, which is equivalent to having an infinite convection coefficient. To having and infinite convection coefficient, or when h goes to infinity. In other words, bi goes to infinity. So if, let's say, instead of having convection on both sides, we say, you know what, we have this infinite slab, and we suddenly change the temperature on both sides from Ti to Ts, or some constant temperature, then what you would need to do, again, we can use the same solutions that we found here, but when we go to the table 5.1, 5.1, then we read the values for u goes to infinity, the C1 and xi. Similarly, for an infinite cylinder, we can find solution for an infinite cylinder. Generally speaking, let's say if we have a cylinder here, that's a long cylinder, and it has a radius of r0 and length of L. When r0 over L is, or the other way, where L over r0 is greater than 10, we call it an infinite cylinder. I'm gonna write it with convection. So if we develop that one for Fourier number greater than 0.2, we can have the approximate for the first term of the series that you find in terms of the solution. We can have an approximate solution where theta star is C1 exponential of minus pi1 square Fourier, and here for the space, instead of having the cosine that we had, we have Bessel function of pi1 r star. Okay. And this is the variable with time, and it is the variable with space, or r star. For the center line temperature at the center of this cylinder, center line temperature at r star equal to 0, what you're going to have is theta star would be C1 exponential of minus pi1 square. Again, we use table C1, 5.1, which for each byte number, it gives you the value of psi1 and C1. And the Bessel function, there is a table that gives you the values of Bessel function for each argument that we have, for each values that we have here inside the Bessel function. We can find out what would be the value of Bessel function. So J0 is Bessel function, and you can find a table in appendix B4. Now, in terms of the full solutions, or exact solutions for this radial geometry of theta star, r star, and t star, with full solution with full series or this complex series is equation 550A in your text. Similar to what we discussed here, for an infinite slab, for an infinite cylinder where the surface temperature is suddenly changed to a constant, let's say Ts. So initially it is at Ti and then it's constantly changed to Ts. We can use the approximate solution, the above solution is also valid, considering that this situation, that the surface temperature is reached to the constant, is equivalent to have an infinite heat transfer coefficient. Also valid, considering that for that part, it means the Biot number goes to infinity. Similar to the other ones. And then we can read the values of Xi and C1 from table 5.1. So we read Xi1 and C1 from table 5.1.